So today we are going to be solving Cambridge O-Levels Chemistry Paper 4 Alternative to Practical May-June 2025 and Paper 42. So this is going to be a hard paper. Before starting, I'd like to tell this is indeed a hard paper. Okay? It's not going to be an easy one. So if you find anything that's difficult or you cannot understand, don't think it had a very low threshold as well, this paper, because it was not easy. So the question one states, a student investigates how the solubility of solid potassium nitrate varies with temperature. Okay, so now what the student's trying to investigate is how the solubility of this substance, this is a salt, is going to vary as you increase or decrease the temperature. The student puts 100 cm cube of water into a beaker at room temperature. Okay, so let's try to visualize what the student is going to do. He has a beaker, he has put 100 cm cube of water in it, measures the mass of the beaker of water, adds some potassium nitrate to the water. Okay, he measures the mass, adds potassium nitrate, stirs the mixture until all the potassium nitrate dissolves. Repeat step 3 and 4 until a small amount of undissolved solid remains in the beaker. Okay, so now what the student's doing, he is adding continuously potassium nitrate in it, and he continues to add potassium nitrate until he sees that there is a small amount of undissolved potassium nitrate left at the bottom of the beaker. Okay, measures the mass of the beaker of water and potassium nitrate. Repeat steps 1 to 6 using water different temperatures. Calculate the mass of potassium nitrate dissolved in water at each temperature. Okay, so we know that as the temperature is going to increase, the mass of potassium nitrate should also increase, because as the temperature increases, the solubility increases. The student does not make an important measurement. State the measurement that the student needs to make. Okay, so student is missing something in this experiment. You guys, if you guys are gonna appear in this May, June, or in October, November 2027, or May, June 2020, 6, sorry, not 7, 6, I'd highly appreciate if you try to think about these questions yourself. State the measurement that the student needs to make. Look what he's missing. He had added the potassium nitrate, okay? He has measured the water. He has measured the volume of the water, added potassium nitrate, measured the mass of potassium nitrate, but he's not measuring one very important thing that he's measuring, that he is trying to determine with temperature. And he's not even a single time it's written over here that he has measured the temperature. It's written repeat step 1 to 6 using water at different temperatures, but didn't measure the temperatures. So the thing that's missing is gonna be your temperature. He needs to measure the temperature to ensure that things are going smooth. Okay, the student results are shown in table 1.1. Okay, at room temperature, this much potassium nitrate is going to dissolve. At 15, this much, and as you increase the temperature, the solubility increases. So over here, it's written that at 55, what's going to be the mass that's going to be dissolved? Estimate the mass of potassium nitrate. So if we try to make a reasonable estimation, for estimation, we need to look at the difference between the two values. Like, how's the difference increasing? So if we look the difference between 31.7 and 54.9, let's see it. 31.7 minus 54.9, and that gives me almost 20 difference over here. Okay? And over here between these two values, what's the difference? 152.4 minus 225.3. 154 minus 223, we just need an estimation. It's almost 70. So now you see what's happening. As you increase the temperature, the difference in the mass is increasing. Okay? Now look at the difference over here in the first two values. Look at the difference. It's gonna be 26 minus 31.7, 26 minus 31.7, 5.7. So almost 6 difference over here. You see over here the difference was 6. Over here the difference was 20, and over here the difference was 70. So the difference is increasing. So if you take the difference over here to be 6 or 7, that's going to be wrong. You have to look at the trend, what's happening. So the difference is obviously going to be almost, we say, between 20 and 70, almost 50 can be the difference. Okay? 50 can be the difference. So 54.9, this is the value, plus 50. That's approximately going to give me 104.9. So I believe that's going to be my estimate, 104.9. And that's not what I've just made randomly. I've looked at the differences. The student observes that when the sodium solution made at 75 degrees Celsius was left at room temperature, a solid appears in the beaker. Explain why. Because the solubility is going to decrease as the temperature is going to drop. Because look at the marking scheme as well for this question, that this solution is cooled, the solubility of the potassium nitrate decreases at lower temperature. So what's happening is that when you heat it, the solubility was increasing. So when you're going to cool it down, what's going to happen? The solubility is going to decrease back. Okay? So what's happening is that it's getting cooled. You're cooling the solution. So white crystals are going to appear of the excess that you tried to dissolve in it because of extra heating. Because at room temperature, only this much can dissolve. So if you have this much dissolved, so when you're going to cool it down back to room temperature, only this much is going to remain dissolved. All the rest is going to turn back into a solid. So I hope you understand this question. You can simply write that your solubility decreases as temperature increases, as temperature not increases, as temperature decreases, and secondly that it is being cooled down. Okay, suggest why the student does not do the experiment at 115. How can he do the experiment at 115? Don't you think he's doing the experiment in water? Yeah, he's doing it in water. At 115, the water is going to boil off. So you have to tell that boiling point of water is 100 degrees Celsius. Above this temperature, there's going to be no water, so you cannot do it at this temperature. Explain by the method the student uses to give a higher value for the solubility than the true value. Look, there's a problem in this method. It's giving a higher value of solubility. It's telling you that more solute is dissolved than reality, and that's correct. Because what he is doing, there is some undissolved solute at the bottom which he is not taking into account, which he thinks that I don't know what, but this solute is not being taken into account. The mass of this is also being measured, though this is not dissolved. So you have to tell that the reason for this is that there is some undissolved solute at the bottom, whose mass is being measured. So additional mass is being measured than what's reality. Additional mass measured, even though that's not being dissolved, still the mass is being measured. Okay, solid W is an impure organic acid, H3A. A student determines the mass of H3A in a sample of W by titration with 0.100 mole per dm cube of sodium hydroxide. Okay, so now you need to keep everything in mind that's happening. Firstly, a student determines the mass of this thing by titration in a sample of W by titration with this of sodium hydroxide. Okay, these are the steps the student carries out. Places a sample of W in a beaker, uses measuring cylinder to add 100 cm cube of distilled water into the beaker, stirs the mixture until no solid is fully dissolved. Okay, labels the mixture X, pipettes out 25 cm cube of NaOH into the conical flask and adds 5 drops of thermophthalene indicator. Okay, so now a lot is happening, you need to visualize it. First, he places a sample of W in beaker. Okay, he takes a beaker, places a sample that's called W in this beaker. Okay, this is W. Uses a measuring cylinder. Okay, so now he has this measuring cylinder. Okay, he has this measuring cylinder to add 100 cm cube of distilled water into the beaker. So now from this measuring cylinder, he adds water into this beaker. So this is water and this is W. Okay, stirs the mixture until solid is fully dissolved. So now he's basically gonna take this and mix the mixture like this, and this W solid is gonna dissolve into the mixture. Okay, so now this W is basically dissolved in the water. So this is the water and W is dissolved in it. So dissolved in it. Done. Stirs the mixture. Let's just remove and draw only water. Okay, stirs the mixture, labels the mixture as X. So now this mixture is labeled as X. Next, pipettes 25 cm cube of NaOH into conical flask. Okay, so now basically he has this conical flask in which he pipettes out 25 cm cube of NaOH and adds 5 drops of thermophthalate indicator. Okay, so now from above he's adding 5 drops of indicator in this flask, and we know one thing, that what is the color of thermophthalate in alkali, because in the conical flask we have our alkali. So what's going to be the color? Thermophthalate is blue in alkali, so there is going to be a let's make a light blue shade from here. Done. Okay, this one's fine, I guess. So basically the thermophthalate is going to turn blue. Now fills the burette with X. Now he takes this mixture that was labeled X, fill it in burette. So now we're going to perform a titration. Let's move our apparatus over here. And now what we're going to do, we're going to do some titration. And how we're going to do titration? Above we're going to have a burette like this. And in the burette he's basically taking this X mixture. So what he does is he basically takes this mixture and he's gonna move it here, and now he's gonna put this mixture into the burette. So this burette is filled with X. Okay, and what was X? X was basically your W that was dissolved in 100 cm cube of H2O. Need to make sense of everything that's happening. Adds X to the conical flask until the solution just changes color. So now what's going to happen? X is basically something that's going to be acidic. Why it's going to be acidic? Because W has an organic acid H3A in it. So W had H3A and we made X from W. So this X is going to be acidic. So now when you're going to add acid to this drop by drop, what's going to happen? That thermophthalate in acid is colorless. So finally this mixture is going to turn colorless at one instant. When we're going to keep adding this keep adding this acid from the burette drop by drop. Okay, so this is going to turn colorless. Now what he says, and repeats the titration 2 more times. Explain why it is important to use distilled water, not tap water. For this experiment, tap water has dissolved salts and impurities in it, so we never use tap water in our chemistry lab experiments. We tell them that tap water has dissolved salts and impurities, dissolved salts that are not good for the experiment, so we avoid it, and impurities, like there are going to be dissolved salts in it, like chloride ions, or there can be some sodium ions in tap water which are going to ruin the experiment. Okay, figure 2.1 shows the initial and the final burette reading. Okay, so how do we read the burette? Do we read the burette from below or do we read the burette from above? That's a very big misconception, I guess. We always read the burette from above, because what's going to happen is that from below it's going to drip out. So from above or below, देखो, what's gonna happen is that your mixture is getting out. So if this is your burette, okay, if this is, just think about it like this. If this is your burette, over here it's 0, over here it's 100, okay. What's happening is that slowly the amount is gonna reduce from 100 to 87, right? For instance, it reduces to 87. So now what you're gonna do, you are gonna read 87 from below, or you're gonna read 87 from above. Think about it. If the level falls of the mixture, so you're gonna try to read it from above. Why above? Because you've only used this much, you haven't used this much. That's what you need to understand. So it's gonna be 4.1, this one's 4.2, here a 4.2, and here is 23.567, 23.7. So let's now note it down. Titration 1, final burette reading was 23.7 and initial was 4.2. Is it correct? Yeah, 4.2 and 23.7, because if we mess this up, we're going to mess the entire question. Volume used. How do we find the volume used? We subtract the two readings. So 23.7 minus 4.2. This is, by the way, a difficult mole question because I'm going to tell you in the later parts. It's going to be difficult. 19.5. 19.5 and 19.2 minus 0.1, that's going to be 19.1. And 38.6 minus 19.3, 38.6 minus 19.3, and it's going to give me 19.3. Now best titration results are going to be those results that are concordant. What is concordant? Means that they have a less difference of less than 0.2. So now if you look over here, and over here, now you need to realize the difference. Okay, so if we look at the difference between the results over here and over here, we have a difference of 0.2, and between 0.1 sorry, so 0.2, and between 19.3 and 19.5 we have a difference of 0.2. So which results to take as the best results? So it's not possible that we get the same, because I know it's not possible. So now I guess I have made a mistake in calculating. I'm going to calculate this again. 23.7 minus 4.2. So 23.7 minus 4.2, and that gives me 19.5. Now let's check what mistake I'm making. This is 23.5678. Yes, that's my mistake. That's how you figure out your mistakes from the exam paper. 23.8. Look, I figured it out. So because of my results, 23.8, my results forced me to figure out, because I know that if these two have a difference of 0.2 and if these two have a difference of 0.2, it's not possible. Examiner is not trying to trick me over here. So it's 19.6. So now which two results? This and this, because they have a difference of 0.2. 19.3 and 19.6 have a difference of 0.3. And by the way, you need to be careful about this reading. The mistake I made, try not to make it. Okay, use the best titration results to calculate the average volume. So the average is going to be 19.1 and 19.3 are two results divided by 2, which is going to give me 19.2. To calculate the number of moles of NaOH in 25 cm cube of 0.1 mole per dm cube of NaOH. Okay, so now 25, which is the volume, multiplied by the moles, which is 0.100, and we divide the volume by 1000, because we know one thing, that we have to take the volume in dm cube, not in cm cube. It's in cm cube, so we divide it by 1000. So 25 times 0.1 divided by 1000. 25 times 0.1 divided by 1000, and that gives me 0.0025 moles. So my moles comes out to be 0.0025. Okay, the equation for the reaction between this and this is shown. So now what does the equation tell me? Equation tells me that 1 mole of this thing is going to react with 3 moles of NaOH. So calculate the number of moles of H3A that we're going to react with these many moles of NaOH. I know that my ratio for H3A ratio NaOH is 1:3. So if I have 0.0025 moles of NaOH, which I figured out over here, I'm gonna have X moles of H3A. So X is gonna be 0.0025 divided by 3. So 0.0025 divided by 3, which is 0.00083. Okay, 0.00083. Okay, I just tried to write it till 3 decimal places. Why? Randomly. Or you can write till 2 decimal places, because these zeros are insignificant, not significant. Okay, not decimal places, two significant figures I tried to write it. Okay, calculate the number of moles of H3A in the sample of W. Okay, so now these many moles were in a sample of X. Okay, in the sample of X, and you need to realize that how much of X we used, how much of X we used, how much we used. The Bird reading told us that we use 19.2 cm cube. So first we need to find out the we have the moles, we have the number of moles of H3A basically in 19.2 cm cube. Okay, these are the moles that are in 19.2 cm cube, because we used this much volume and in that we had this much moles that reacted. So 19.2 cm cube basically has 0.000833 moles. So how much volume was made from H3A volume was made from W? A sample of W was placed and the volume of that was 100 cm cube. So how many moles are going to be there in 100 cm cube? Let's figure it out. So 100 cm cube is going to have x moles. X is going to be 0.000833 multiplied by 100 divided by 19.2. So this number multiplied by 100 divided by 19.2, and that gives me 0.00434. 0.00434. Done. Okay, the relative molecular mass of H3A is 210. Calculate the mass of H3A in the sample of W. Okay, so mass formula is simple. Mass equals to my moles multiplied by my MR. My MR is 210 and my moles were these many, 0.00434, 0.00434. So my answer comes out to be multiplied by 210, it comes out to be 0.91 grams. 0.91 grams. Simple. Okay, in step 2, these moles might be complicated for some of you, but for me they weren't that challenging. But if you guys are beginners, gotta practice moles for ATP especially. In step 2, a measuring cylinder is used to add 100 cm cube. That's not very good. Why? Because measuring cylinder is not that accurate. Explain why using a measuring cylinder makes the volume of the distilled water is inaccurate. Suggest an improvement. So explanation is that measuring cylinder has a lower precision, okay, is less precise, and the improvement can be that we can use a pipette, or a more good word can be we can use a volumetric pipette, because what a volumetric pipette is going to do, it's going to measure exact volume. Before the student does step 6, the burette is rinsed with distilled water, and then with X, explain why the burette is rinsed with distilled water. So what you're doing is that you're simply rinsing it with water. So what you're doing, you are simply removing any unwanted substance or impurities that you have. That's why you wash with water. You wash anything with water to remove impurities. Now what's going to happen, suggest and explain the effect on the titration results if the burette is not rinsed with X after rinsing it with water. That was what I was thinking about, that this is not a good thing if you just rinse it with distilled water. You need to rinse it with X as well. Why? Because look, if you only rinse your burette with water, there are going to be some water particles left on the surface of the burette. So now when you're going to add your solution is going to be diluted by the water that is going to be present at the surface. So the effect is going to be that your volume of X is going to increase. Why? Because now this has become dilute, so you're going to require more of it. So you're going to say volume of X increases. That's used for titration, and the explanation for this is going to be X becomes diluted. Why it becomes diluted? Because you've rinsed it with water, and now there are going to be some water particles over here, so you need to rinse it back with the solution X. Okay, I guess this is going to be tricky. A student investigates solid A and aqueous solution B. Solid A is a metal carbonate. Okay, so now we know solid A is a metal carbonate. So if we added an acid, what kind of gas are we expecting? We're expecting carbon dioxide gas. Solution B contains only one cation and one anion. Okay, one cation, one anion, it's a solution. Student does a flame test on A. Describe how to do a flame test. Okay, so how do you do a flame test? You take a wire, okay, and you basically dip it in the solution, okay. Does a flame test on A, and A is a metal carbonate. So basically, if we say it's a group 2 metal carbonate, it's going to be insoluble probably, okay? Or if it's insoluble as well. So what you're going to do is that we're going to do it with the solid, okay? Now we not have a solution because we're expecting it to be a solid. So wire dip in the solid and then we put it on a blue Bunsen burner flame. Why we put it on a blue Bunsen flame? We also call this a roaring flame. Why do we call it a roaring flame? Because this is necessary. If we put on the yellow flame, we're not going to get our results because the results are going to be basically camouflaged by the flame color. So we need to use a blue Bunsen flame for this. A student observes a blue-green color in the flame, identify the cation present in it. Okay, go to the list below. Blue-green color. Where's a blue-green color? That's a blue-green color. So it's going to be a copper 2+ ion. Okay, a student basically observes blue-green, so it's going to be a copper 2+ ion. Next, the student adds dilute HCl to A. A was a metal carbonate. So now I told you that if you add HCl to a MgCO3, this is a metal carbonate, you're going to form carbon dioxide gas. An aqueous solution C and a colorless gas is formed. Describe the observation the student makes. Describe the chemical test and the positive result used to identify the gas formed. The observations are, firstly, there's going to be effervescence. Secondly, you're going to see the solid disappears. Okay, and now you have to tell the test for gas. Go down, check the test for your very own carbon dioxide gas. Where's carbon dioxide? This is turns lime water milky. So that's going to be the result. The test is going to be add lime water, and the result is going to be that lime water turns milky. Okay, explain how the student knows the reaction has finished. When the effervescence will stop. Effervescence stops, okay? When the bubbles are going to stop. In the bubbling reactions, you always know the reaction's over when the bubbles stop. Okay, explain how the student uses aqueous ammonia to confirm the metal ion present in C. Include the observations you expect. Okay, so now how the student's gonna use ammonia. So basically we know that ammonia is gonna produce, if we look at the what he's trying to identify, look, he knows what is the metal compound present in C. Look at C. What's C? Solid A. C was, the student adds HCl to A. Now HCl added to A. A was a carbonate. Carbonate plus HCl add an aqueous solution C and a colorless gas is formed. So now C is gonna have C is gonna be some metal chloride. Do you get it? Because over here what you're gonna form, carbon dioxide plus metal chloride plus water. So C is gonna be a solution of metal chloride because carbon dioxide is gonna escape and water is gonna have no effect. So it's a metal chloride. So now we have to tell that how are we gonna know that what metal ion is present by adding ammonia to it. Okay, we already know that there's a chloride ion in it. So over here, look, we were doing one thing that you need to realize, that in A we basically had a copper ion which we figured out. So don't you think one thing, that this metal carbonate is gonna be your copper carbonate? Don't you think this? It's gonna be CuCO3. I think it's gonna be like this. And since we dissolved this copper salt, solution C was made up of copper, so with effervescence and the solid disappears, what else observation? Because we're dissolving a copper carbonate, there's gonna be a blue color solution formed. Okay, we're having a copper salt. This part told us that it was copper. Okay, so with ammonia, we have to confirm the metal ion present in C. Let's read ammonia's observation and copper. You just have to copy the slide. Blue PPT insoluble in excess, not with aqueous. You just have to give this entire thing. That's going to give you 4 marks. Light blue PPT soluble in excess, giving a dark blue solution. So just write this like as it is. Light blue PPT soluble in excess, giving a dark blue solution. Okay. The student does a test on B. The results are shown. Identify the anion and B. Okay, adds dilute nitric acid and aqueous barium nitrate colorless solution. That means there is no sulfate present. That's a test for sulfate. Add dilute nitric acid, then add silver nitrate, cream precipitate form. That means there's a bromide. And add aqueous silver hydroxide, aluminum foil and worms. Colorless solution formed. Nothing. There's gonna be a bromide ion over here. Okay. Okay, Q is a mixture of solid copper carbonate and solid lead sulfate. Okay, so now Q has copper carbonate and lead sulfate in it. Copper carbonate and lead sulfate. Writing down the formulas: CuCO3, TbSO4. Lead sulfate is insoluble in water and does not react with dilute sulfuric acid. Okay, good for us. Examiner has told us this. That means it might be important in the future. Copper 2 carbonate is insoluble in water. Okay, copper 2 carbonate is also insoluble in water. It reacts with dilute sulfuric acid to form copper sulfate. Plan investigation to obtain pure copper sulfate crystals and pure lead sulfate crystals to form Q. Your plant should use common laboratory apparatus, dilute sulfuric acid and Q. No other chemical should be used. You should include the apparatus, the preparation, the method, and how to test the lead sulfate is pure. Okay, so the first thing we know that, let's draw it over here. Okay, we have lead sulfate, PbSO4, and we have the second mixture, that is copper carbonate, CuCO3. So now this is a mixture which has lead sulfate and copper carbonate. Okay, so now that's the mixture that we basically have. So what are we going to do? We know that this lead sulfate, this is insoluble in both water and copper carbonate. So what are we going to do? We are simply going to take a container, add this mixture into the container. Okay, add this mixture into the container, and then what we're going to do, we're going to add water. What's going to happen? This pink lead sulfate is insoluble. So what's going to happen? These white particles, they're going to dissolve. The white particles are going to dissolve. And these pink particles, they're not going to dissolve in water because the white particles were your copper carbonate. These were the white particles. So these white particles, they're going to dissolve. So what happens is that your lead sulfate is left over here. And now what you can do, you can simply filter out these pink particles on a filter paper. And over here, now you can dry them, wash them, dry them, and you get your lead sulfate. And now to check its purity, how are you going to check its purity? You're simply going to check its melting point or boiling point, because a pure substance has a fixed melting point and boiling point. Simple. Now comes about the part 2, separate copper carbonate. What are you going to do? You know copper carbonate is going to react with sulfuric acid. So you're going to you have to obtain copper sulfate, not carbonate, right? Copper sulfate. So what are you going to do? Take copper carbonate. Okay, so what are you going to do? You're going to take your copper carbonate, CuCO3, add sulfuric acid to it. This is H2SO4. Reaction is going to happen and your copper sulfate is going to form. Now this copper sulfate is basically inside the solution. So what do you do? There is an important thing, that you are going to add this copper carbonate in excess. Why in excess? Because you want to make sure all the sulfuric acid is used up. When you're adding it in excess, you always know that when you're forming a salt from an insoluble carbonate or metal, you add the acid in excess because you want to make sure that all your acid is used up. So what you're going to do now? You're simply going to now perform your crystallization on it after filtering out this insoluble salt. So what do you do with this insoluble copper carbonate? You filter it out. So you filter it out, your copper carbonate gets removed. Now you simply have the solution of copper sulfate. So the copper carbonate basically comes over here. This is your copper carbonate that's filtered out. Now you have copper sulfate. What do? You crystallize it. And how do you crystallize something? You basically heat the crystals, heat the solution in a evaporating dish with a flame beneath. You're gonna heat it. What's gonna happen after that heating? What you're gonna do after heating? You're gonna cool it down, and when you cool it down, there are gonna be some crystals forming on it, and those crystals will be copper sulfate crystals. And then you can dry the crystals between sheets of filter paper, and like this you're gonna have your copper sulfate form. And that's it for this video. You just have to write this experiment words, and for the apparatus you can simply tell beakers and filter funnel and all that thing. So done and dusted.